Good afternoon, everybody. I'm going to start this lecture with you. Um, I want to answer to the question on the chat. Yes, I'm going to charge the material concerning the exercise number 4, and I will publish this material today in the afternoon or maximum tomorrow. So let's go with our lecture, and I want to talk about today on issue concerning the gust response, and we have developed a model for gust model, linear model. Consists of a transfer function vector like AG, such that applied to an input velocity vector profile is able to give us as output, we have W scalar vector, to give us the vector of the model coordinate Q. Okay. However, this is the basic model we developed, and today I want to clarify two issues. One issue on the physical type of possible output, that can be defined. We essentially have as output the model coordinate by model coordinate, and then second input, second issues is on the input output type possibility in terms of deterministic or stochastic process. Okay, so as concerning the first issue, we have, of course, the model coordinate. First of all, the input. The input for the gust is the velocity profile. And we clarified this in the model of Taylor gust model. In the Taylor gust model, we started by a complicated scenario in terms of like this, for example, in terms of gust. We may have a distributed turbulence scenario, but at the end of the story, we have a unique scalar time profile for the velocity. We know that in this model we have a frozen gas model, no variation in span-wise, wingspan-wise direction, wingspan direction, and small geometric length of aircraft very less and less with respect to the geometric characteristic length of gust. At the end of this, we have as input a unique value for the velocity. We have a velocity profile, which is originally a space function, and this space function became, after this hypothesis, a time function after assuming x equal to u infinite by t, so a function of time, like that. So we start by this, we go to this, and eventually through a Laplace transform, we have a Laplace transform of this function here. Okay, so the input is a scalar time function or a scalar frequency domain or Laplace domain function. Okay, the output in the physical point of view, in the output, we have as direct output, we have the modal coordinate vector. In your analysis. So we have a time vector, for example, modal time vector with Q1, Q2, and up to Q bar M, with M the number of modes included. Consider that typically in gust response, first modes are typically rigid body mode, like vertical rigid body motion or pitching rigid body motion. Vertical rigid body mode, pitch rigid body mode, and these two are the essential one for describing a coupling between elasticity and longitudinal flight dynamics. Okay, first modes are typically rigid body modes, okay, and the other one are the elastic one, okay. So this is the primary output, but the other output may be, for example, displacement, elastic, and how can you have your displacement, elastic displacement? You may consider, for example, the physical finite element displacement obtained by the model one using the modal matrix applied to the modal coordinate, and therefore if you want the displacement, you have just to consider this in Laplace domain, applying your gust to your input. Okay, and this is a new transfer function give you directly the displacement with or the modal coordinate directly by your input. Okay, so you have something like, for example, in the control theory, you have the state space, and in this case, your state space are the modal coordinate, and here, this is the gust vector, and you may have as output something depending on in time domain or in frequency domain, if you prefer. And in the output, you have y equal to c on the state. And so this y, in this case, is this vector, and the output matrix is here given by your model matrix. This is the control theory view of this kind of definition for your output. So elastic displacement is another kind of secondary output, but and if you want to know, for example, the acceleration, the aircraft acceleration, you may have, for example, you can consider your rigid body vertical mode with Lagrangian variable q bar 1 as the first modal coordinate here, this here. And if you want to know the acceleration, you have just to define, as in the Laplace domain, just the second derivative of your vertical rigid body motion modal coordinate, and this is the acceleration output. This is another output. But the last and not the least output is composed by the loads, aeroelastic loads. How can you obtain your loads by your modal coordinate? It's very easy for obtaining the unsteady aeroelastic load by the modal vector q bar. One has to consider the elementary modal loads. What is the elementary modal loads? This is defined as the following. Suppose to concentrate your attention on a specific load, as, for example, the bending moment at the root spin. Consider as output the wing root bending moment. In Airbus, this quantity has an acronym like wing root bending moment, WRBM. And this is very important in aeronautics as a load parameter. Okay, evaluate the wing root bending moment after applying your mode shape. For example, first elastic mode shape, like here, you have this shape in your finite element code. This is the first symmetric bending mode, and here apply this mode shape psi, for example, psi 1, or maybe psi 3, because psi 1 and psi 2 are the rigid body motion imagine of your structure, so you have no deformation for rigid body motion. So consider the first elastic mode, for example, the first symmetric bending mode, psi 3, and evaluate here your wing root bending moment, and call this wing root bending moment as consequent of the mode 3 application, like a quantity, for example, like alpha 3. Okay, then apply the second of this mode, supposed to have a mode shape like this. Second bending, psi 4, and evaluate, impose the mode shapes as given by your normalization decided, unitary mass normalization or maximum displacement normalization, we don't care. Impose the eigenvector you have assigned for your model analysis with the related normalization process. Impose the mode shape, and then evaluate your wing root bending moment here, which is your target. Okay, and the other one should be a torsion, for example, for the wing. So you should have something like a torsion. The wing goes down and goes up like this. This is a torsion. Psi 5. And then here you have alpha 4 and alpha 3. So you have something like elementary load associated to each elastic mode, and you have this coefficient like alpha 3, alpha 4, alpha 5 as modal load associated to each mode, giving you your wing root bending moment. Wing root bending moment. Wing root bending moment. Okay, so these are something like elementary modal loads. Okay, and what happens in the generic case? When you have in the case of a generic input, you should have a final modal vector in time, for example, composed by Q1 rigid body motion. We're supposed to have a rigid body motion as a function of time, Q2 as a function of time, and all the other modal state coordinate. And you know that this value of your wing root bending moment is the value when you have a modal coordinate equal to 1. the action of your mode shape. Okay, so in the general case, your wing root bending moment in time should be something like skip, please, the rigid body motion, and in the case of the last one, so you have 0 plus alpha 3 wing root bending moment by q bar 3 time, function of time, plus alpha 4 wing root bending moment, q bar 4 function of time, plus or the other. Here we are currently applying massively the concept of modal analysis. We are using our modal coordinate for rebuilding our time varying wing root bending moment on the base of the knowledge of these elementary bricks of your analysis. Your modal coefficient associated to your elementary load. Okay, and so this is a last but not least application of modal analysis for obtaining your final load. So in this case, your target output is the wing root bending moment for your aircraft in a mission, and this scalar quantity is easily given by applying this vector, this scalar vector, to your modal coordinate as a function of time, or this is a time function or a frequency domain function, function of S equal to the transpose of alpha. Alpha is collect this coefficient. Of course, the first two coefficient alpha are 0 in the case of rigid body motion. First two are the rigid body motion. You have just to apply this to, and this is your output matrix. I mean the matrix which allows to you to identify your specific output as based on the state space vector modal coordinate vector. Okay, and this is the version in Laplace domain. So here we have a list of possible input and output in terms of physical type of possible variable: velocity, modal coordinate, acceleration, elastic displacement, loads. And these are all the possibility you have on selecting your output in unsteady gas load analysis. Okay, but here we have another relevant issue. The second issue is on the not only on the physical type, but on the signal processing type. We may have a signal in time domain, in frequency domain, or we may have our signal in terms of statistic description as power spectral density or auto and cross correlation. My question now is a key question if you are familiar or not familiar with this kind of description. So item number 2. Item number 2. Excuse me. Whoa. Under number 2, signal type. Possible signal type. First natural is time signal. Second one is frequency domain signal. Third one is Laplace domain signal. And apart, we have two version for stochastic description of the signal, which is correlation signal, auto, self correlation and cross correlation, better. And power spectral density, self and cross. This description is typical for deterministic description of input and output, and this here is typical for stochastic or random time signal, or better, random process. Okay. I know that you are familiar with this concept in telecom theory, telecommunication, or in radar signal, something like that. But this concept are key concept or in mechanics, in structures and elasticity. So this is for the deterministic case, and this is for stochastic one, or random, better. Example, time signal, consider the input. We have a unique input, which is our gas profile, and therefore the time signal is Wt. The frequency domain version is the Fourier transform tilde omega, or better, frequency. So this is W and this is omega, please. And Laplace domain is something like same symbol, but this is depending on S. And this is the Fourier transform of W T, and this is the Laplace transform of W T. Excuse me. The key point is here in the right hand side of these slides, because excuse me, in the right hand side of this slide we have a key question. Okay. How in the description you obtain the output by the input, and here in the frequency domain vision or the deterministic signal we have the output, the essential output, which is given by the model coordinate, which is equal to our frequency response function of omega, applied to the Fourier transform of the input, and you obtain the Fourier transform of the output, okay? Just by an algebraic multiplication. And the same for Laplace domain vision. We have the Laplace domain transform of the output is equal to H S by W tilde S. Here in time, you know, you should have the analytic solution, but you don't have an explicit form, but you just know that you have an equation like this. You have m q dot dot bar plus q bar equal to dynamic pressure integral. You have an integral differential equation with this matrix, which is the inverse Fourier transform of your generalized dynamic force matrix that you have naturally in frequency on in Laplace domain. And you have to take the convolution of this as applied to the state q bar in tau in the tau. So the relationship between input and output is of this type. Okay, and you have to solve this integral differential problem. Okay, the situation is clear in terms of deterministic. And what about what is the typical case of deterministic input for your gust? You have the 1 minus cosine gust. Okay, so your model of the input in the requirement is the 1 minus cosine gust like that. You have a bump in time, and the regulation oblige the designer to check all the possibility bump in terms of amplitude, and this velocity is also known as U gust design velocity, UD, like D is for design. So if you see the regulations like EASA regulation present a set of possible UD gust design profile amplitude to be used in your simulation for test the aircraft response. So using this model, the deterministic model, okay? And in the EASA prescription, you have several UD and you have several amplitude. This amplitude here is in time, but is also in space, like H. H is also known as gas gradient, and this gas gradient is in space, this distance, x, in body frame of reference of this cosine. And so you have a formula like 1 minus cosine. You have 1 minus cosine of 2 pi x by h. So you have different length of your bump. This is the aircraft coming. Okay, h. So check your aircraft response considering several UD, several h, blah, 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 blah. It is your v as a function of x, 1/2 before. Okay, so this is the deterministic scenario for designing your aircraft by considering a possible deterministic gust input profile. But this could be not satisfactory. There are some other instruments for describing gust, and this description is in the framework of random process. In random process, you are not interested on identify a quantity for your input, a specific time input, but you are interested on exploring an averaged time, averaged signal by several kind of time possible input. I want to give you an example. Imagine to have a time function of a process. This is the turbulence. This is the measurement of the turbulence in a day in Ciampino, for example. This is the W in Ciampino for a day. You have this. Take another measurement. You have this. you are several times sampling of the same quantity. Okay. Of course, you could take this sampling. This is the sampling W1, the sampling W2, W3. You have an anemometer in your airport, and you are able to measure your vertical wind velocity for collecting a possible dust input. Of course, you could take this specific sample, take for example, the Fourier transform. You should have probably a Fourier transform a bit chaotic like your sample. Take the Fourier transform, blah, 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 obtaining your chaotic model coordinate. Is this significant for a design? No, at all. Could be more significant, consider an average of this quantity, of this time quantity. And a possible average of this time quantity is a quantity known as the autocorrelation. The autocorrelation function is an average of this quantity obtained by assuming that if you take an average of only the first one, excuse me, only W1. If you take an average considering only the first sample and take an average in this way, this quantity defined like the integral on minus t by 2 to t by 2 of w t by w t plus tau in dt. This is as taking the limit for t going to infinite, is a quantity depending on tau, and this quantity is a measure of what happened in a time here with what happened in a time t plus tau. This is tau. Okay, so this integral is a measure of the correlation of what happened in a time t fixed, what happens in a time t plus tau here. What I imagine is that this correlation is independent on time shift, is a unique quantity. And the assumption I'm doing, assuming this as average, is the fact that my original idea of average, which was an average between the several samples, can be transformed in an average using only one sample. Instead of use several time sample, I can perform my average by using only one in time. This hypothesis is the hypothesis also known as hypothesis of ergodic process. The samples average can be substituted by a time average. Average on the same time function. Okay. What happens randomly in one sample in a long time is the same happens in average, considering several samples of the same process. This is the concept of ergodic process. Okay. Note that this integral is very easy to be computed, and this integral, this function is a regular function. This function is this function of tau is representing the average of your random process. Okay? Let me have one more view graph. And note that the sample, the single sample is random and may be random and chaotic. Its cross correlation is a regular and smooth function of tau. Okay, so for example, you may obtain R tau of your W gas function as something regular like this. Note that this tau is not representing the current time variable. Yes, the dimension is a dimension in second, but is not representing, is not the current time of your process, but is representing the generic distance between one time and another time you are considering the correlation. Okay? This is important. This is important that this function is a regular, a smooth function, and therefore makes sense to take the Fourier transform of this regular and smooth function. Okay? The Fourier transform of this regular function is the power spectral density of signal. And is another regular function. Regular function, not chaotic, I mean regular function 2. Okay. Okay, so the scenario is the following. We have a chaotic input and we have a deterministic system, but after the application of a chaotic input, you should have a chaotic output. And so the question is, what is the relationship between our chaotic input or the statistics of our chaotic input and the statistics of our chaotic output? In particular, in input, we have the autocorrelation of the gas input, or the power spectral density of the power input, which is the Fourier transform of our input. And in output, we have the correlation between any, attention please here, any modal coordinate. We have a multiple output here. Attention please. And therefore, when we consider the correlation in the multiple output, we have to consider the correlation of each component of the output, which itself and the other. So we have a matrix of correlation, Qi, Qj, function of time, defined like limit for t going to infinite of 1 of t integral minus time by 2 plus the window t by 2. And then we have to correlate the I generic model, if you prefer modal coordinate in time, with itself or eventually the other one. So j, qj, t plus tau in dt. Excuse me. And correspondingly, you have a matrix for the power spectral density, which is the Laplace transform of such a quantity. And so we have S, Qi, Qj, and this function is a function of the frequency. Excuse me, it's not a function of the tau, but of the frequency. F omega is equal to 2 pi f. So you can use radian per second or hertz. And so we have a matrix for the output in frequency domain. Okay, and this is the Fourier transform of your R Q bar I Q bar J. Okay, at the end of this very impressive lecture of our scenario, the question is, what about this right-hand side here? What is the relationship between the input and the output of our process? I give the response here for you. And the response is the following. The matrix of the power spectral density of the output, for example, the matrix of the auto across power spectral density of the output Q is equal to the conjugated of your gas transfer function applied to the power spectral density of the input, which is in this case a scalar, it's a 1-by-1 matrix, by the transpose of your transfer function. Okay, so this is the, here you have this in the deterministic case, but in the case of stochastic scenario, the statistics of the output is given by the statistics of the input pre and post multiplied by, here you have the conjugated, excuse me, the conjugated matrix. And you have a double use of your transfer function. You have to pre-multiply the conjugated of H by S, the statistic of the input, and post-multiplicate by the H transpose to have the statistics of the output. This is the general formula used by the random analysis, providing as input the autocorrelation of your gas profile or the power spectral density of your gas profile. And the typical power spectral density of your gas profile in this domain is the von Karman spectrum. And I stopped here. Von Karman spectrum. So you have by the regulation, the 1 minus cosine profile for deterministic input, and then you have the von Karman spectrum for your random input for gas response problems. Thank you for your attention. I know that this framework is very dense with high density information, but I know that somebody of you is familiar with this kind of random description, somebody else not so much, but I hope to have given to all of you a global idea, a relevant idea of this scenario. So thank you and see you the day after tomorrow.